This is the problem about push-ups, and it reads, the drawing shows a person whose weight is 584 newtons doing push-ups. Find the normal force exerted by the floor on each hand and each foot, assuming that the person holds this position. So, what is given is the force as far as the weight is concerned. So the weight is given, but then they're asking what is the force on the hands and what is the force, or each hand, what is the force on each foot. And so we have two unknowns, and that usually means, or almost always means, that we need two equations. We'll see what happens here in a moment. What is given are all the lever arms. Here's one and there's one, and I'll comment on that in just a moment. What is also given is the torque. So, because it says, assuming that the person holds this position, and that means the person is in rotational equilibrium, and therefore the torque comes out to 0. So I can write this down, that the torque comes out to 0. But first I need to make a decision of what is my rotational axis. It turns out actually if I keep my rotational axis here, or here, or here, or anywhere, it actually doesn't matter where I put it, because the torque being 0 everywhere means that around any kind of rotational axis, for example in the shoulder, or the hands, or the feet, or the center of gravity, or in between, must come out to 0, because otherwise if it wasn't, if he would be for example pushing harder on the floor, and the floor would be pushing harder on him, therefore he would go up and we would have a rotational torque, but that's not the case. He's holding the position, so the torque has to be 0. The combined torque has to be 0 everywhere. I just decided to use the center of gravity as the torque, and therefore I have the force exerted by the feet times the lever arm for the feet from the center of gravity, plus the force for the hands times the lever arm from the hands to the center of gravity. And here I need to note, if this is my rotational axis, then I have to consider this lever arm here to be negative. So I keep that in mind, that this one is negative, and of course this one is positive. And the two forces that I'm interested in, this one here, this is the force by which the floor pushes on him, that's what we're interested in. That points upwards and therefore is considered positive. And the feet here, this is not the scale, are also pushing upwards. Of course the hands are pushing down on the floor, but we're interested in the force being exerted on the person, therefore the torque exerted on the person. And this would make sense here, therefore this one here will become a negative and this one would be a positive, and then those negative and positive torques will come out to 0. In any case, we do have two unknowns here, force of the feet, force of the hands, but we need a second equation. And that second equation is that he is in rotational equilibrium, but he is also in just equilibrium, and that means that the forces that are acting on the person also come out to 0. So the original Newton's second law plus 4, and here we don't have a rotational axis, and so therefore the weight figures in here. By the way, the weight would have figured in here as well, but since to the torque equation, but since I chose the center of gravity to be the rotational axis with a lever arm of 0, therefore I didn't write here weight times 0 in here. But yeah, it actually is there. It's just 0 itself because the lever arm is 0. Okay, so here we have the feet up, the hands up, and of course the weight down, and that means that this one here is a negative as well. So we have two equations in those two variables, so we substitute from one to the other. So for example, if I write force of the feet plus, and now I substitute from the first equation force of the hands in there, I get this to the other side, which introduces a negative, and then I divide by the lever arm from the hands. So actually this one here comes out to be a negative. So I'm going to have force of the feet minus lever arm F divided by lever arm H times force of the feet. And you should be able to see that when I solve this one here for force of the hands and substitute in here, then this is what I get. And then plus the weight, and that equals 0. That's a really bad looking plus. Try this again. There, that's better. Keeping in mind again that this LF here is actually negative, and then this one here is negative as well. And now I solve for the force on the feet. I get the weight to the other side, which introduces yet another negative in the algebra. Divide by this one here combined, which is 1 minus LF divided by LH, and then equals, and then there's the answer, and that should be in newtons, of course. Now you see that there is quite some algebra involved here, but of course this is an algebra based class, so I expect of students that they're able to follow the algebra that I did here and can actually reproduce it. Again, a note here, this negative and this negative here were introduced from doing the algebra, putting it to the other side, and then this W itself, the weight here is negative, so actually we have a positive number here, and then here the LF is negative as well, so actually we have a positive here as well, so we divide a positive by a positive, which of course comes out to a positive force, which makes sense because the force on the feet is pointing up. And then for the force of the hands, I guess the easiest equation to use here would be the second one, where it then says force of the hands equals minus the weight, again this one here being negative, minus the feet. So here this one is actually a positive number, as I said, and then from that I subtract that positive number here, and it so happens that the force of on the hands then comes also out to be positive in newtons, of course. And then lastly you would need to calculate 1/2 force of the feet and 1/2 force of the hands, because they say on each foot, on each hand, and what I did here is I calculated the force on both feet and on both hands, therefore at the very end divided each by 2.